we are going to study a section that has got a subtopic that reads the second derivative. The second derivative. Now you remember we found f dash of x, and now we are saying we are moving from f dash of x, which is the first derivative, we are deriving for the second time, and this is the symbol that we use when we talk of the second derivative. Now, boys and girls, I want you to understand that when we are talking about the second derivative, we use the second derivative to identify stationary points. So we can use the second derivative to identify stationary points. And concavity. Of any graph without sketching it. So it is very important for us to understand that whenever we are finding how the graph is curving and we want to identify stationary points, remember, points of inflection are stationary points, and points that are on the turning point are also stationary points. So we'll deal with these points as we employ the second derivative. I want you also to understand that the second derivative is very important, especially when we are talking about points of inflection, as you'll notice. But let's start with how to identify stationary points. We want to identify stationary points. In other words, we are saying, how do we identify stationary points? Now, I want you to understand that we can actually classify and identify stationary points by doing the following steps. So the first step is to solve for x. We are solving for x in the statement f of x, f dash of x is equal to 0. Now, when we are solving for x here, we are finding the x coordinate at the turning points. The x coordinate at the turning points. Number 2, if we solve for x and we get x is equal to a or b, let me highlight before I proceed here to say we are actually dealing with cubic functions. That is why our x has got two values. When you differentiate for the first time, we get a quadratic. And when we solve a quadratic, we get two equations. We get two solutions rather. We get two solutions. That's why I'm saying in general, we have solutions x is equal to a or x is equal to b. Now, to talk about the concavity, or to discuss whether the graph is increasing or decreasing, we identify the behavior of f dash of x to the left of our turning point, which is A or B, and then to the right of the turning point, which is either A or B in this particular case. So when we find f dash of x for x less than A, we also find f dash of x for x greater A. You see, A is the turning point where the graph is either minimum turning point or maximum turning point. These two values can actually inform us whether the graph is increasing or decreasing. Now, if f dash of x less than A is, say, a value that is negative, then it means the graph is going down. And when this one is greater than 0, it means the graph is going up. So this side is f dash of x less than 0, and this side is f dash of x greater than 0. Please take note of that. Where at this point we have x is equal to A. So if that is so, then it is actually informing us that this here is having a negative gradient, because remember, f dash is the gradient from our previous study. And on this side, it means f dash is positive, which means it's an increasing. This part is decreasing, that part is increasing. So once we have that, we can say we have a local minimum turning point, and hence the graph is concave up. As you can see from this graph, it's curving up, as opposed to curving down. This is curving down and this is curving up. So we say graph is concave up. Here we conclude that graph is concave up. Very important. And here, remember, this is x is equal to A, and here is our f dash of x less than 0, and here our f dash of x greater than A, rather, not 0, greater than A. So here the gradient is negative and here the gradient is positive. So it started being positive and then it's negative, which means we have a local maximum, and therefore the graph is concave down. Very, very important for us to understand if we are to answer questions without much difficulties here. Number 3, if f dash of x is equal to f dash of x greater than A. In other words, when we have a situation where f dash of x is less than A, being equal to f dash of x greater than A. In this case, we have a point of inflection. We have a point of inflection. Very, very important. A point of inflection. In other words, we are saying the gradient of f dash of the graph to the left of A and to the right of A is the same. That's what we are saying. So the graph will be of this form, where our point x is equal to A, and this is f dash of x less than A, and that side is f dash of x greater than A. So we have identified very important concepts here, that the first derivative can be used to identify whether a graph is increasing or decreasing. and whether we have a concave up, that is, we are now talking of the concavity of the graph, or we are talking about concave down or concave up. So concavity can also be discussed through the first derivative. Important again is for us to notice that if f dash of x is less than 0 for x less than a, and f dash of x greater than 0 for for x greater than a, then the point a, f of a, is in actual fact a local minimum, which means once we say a local minimum, it means graph is concave up. So we have concave up. Now again, if f dash of x is greater than 0 for x less than a, and f dash of x is less than 0 for x greater a, then the point a, f of a, is a local maximum. And we said it's concave down. Concave down. Very, very important for us to understand. Now, I have explained these three graphs already. So let's move on to the next part. We use the second derivative to determine the points of inflection and concavity. Again, instead of using the first derivative test, we are now using the second derivative test. And second derivative is f dash dash of x. We are saying we want to use this to determine the points of inflection as well as the concavity of a function. Steps to follow. I will put all these steps on your platform so that you can read for yourself as well. First, you find your f dash dash of x and equate it to 0. That's number one. Then you solve for x. In other words, we derive the given function twice and then we solve when we equate it to 0. Number two, if f dash dash of x, of a rather, if f dash dash of a, that is the point where we have a stationary point, is equal to 0, then we determine the sign of f dash dash of x. We want f dash dash of x less than a. In other words, we are finding a number to the left of a, then we substitute it into f dash dash, which is the second derivative. But that number that we are using is very close to a. We do the same again to the right. In other words, we are finding f dash dash of x greater a, and we notice that the value of f dash dash of x to the left of a, say it's negative, then we know is concave down. And if f dash dash of x to the right of a is, say, positive, again we know it is now concave up. Please get to understand that. F dash dash of a to the left is negative, it means it's concave down. F dash dash of a to the right of x, it will imply that we have concave up. I think at this point, I then need now to emphasize the importance of using the second derivative. It's short and easy to follow. If f dash of x changes sign, now we are saying if f dash of x changes its sign, that is number 3, it changes its sign, then the point A, f of A, is a point of inflection. Very, very important when you are using f dash. Then we are now talking about concavity. There are steps to follow, and I'm going to give you only 2 steps here. The first step says solve for x if f dash of x is equated to 0. We are solving for x. After doing that, if f dash of a, that is number 1. Number 2, if f dash of a is equal to 0, we then find f dash dash of a. Now, once we have that, we now analyze what we have. If f dash dash of a is greater than 0, then we have concave up. And if f dash dash of a is less than 0, we have concave down. I'm going to look at an example in the next video. I don't want this one to be too long, so just go through it, understand what I've said, and also read the notes that I'm going to post for you to understand what's going on.